Alrighty, so this video is regarding problems that make use of the third law of motion. If you remember what the third law said, it said for every action, there is an equal and opposite reaction. And what does that mean in practice? It basically means when one object applies a force to a second object, that second object must be applying the exact same force back onto the first object. So, for instance, let's say, here you are, here's the floor, you're standing on the floor. You have a weight, which is mg. And of course, you know your weight pulls you down. So there is some force due to gravity called the weight, which is pulling you down into the floor. Now, obviously, you're not falling through the floor. If we consider Newton's second law, which says the sum of the forces equals ma, if this is the only force that exists in the system, then you'd say, okay, there's a force acting on you, which is mg downwards. That's the only force there, so that must be equal to ma. Solve for the acceleration. The acceleration must be g, which is 9.8 downwards. So this would say, if gravity is acting on you, you're standing on the ground. If there's no other force involved, you must be falling downwards with an acceleration of 9.8 meters per second squared. But of course, there you are standing there. You're not falling. You're not moving downwards. You're not accelerating downwards. Thus, by Newton's second law, there must be some other force acting on you. Not only must there be another force, but that force must be exactly as big as your weight to balance, and it must point in the opposite direction to gravity. So there must be some other force pointing up on you, and we'll just call it N for now. We know eventually we're going to call it the normal force. And so so this is wrong. The correct thing to say is, acting on you is your weight pulling you down, but then there's some other force which is pushing up on you from the floor. That's equal to ma. And if n happens to be the same amount as your weight, then what you get is minus mg from your weight, plus the normal force, which is also mg, because we're saying it must be the same size. That's equal to ma. Well, this cancels this, so you get 0 equals ma, which tells you your acceleration must be 0. You're not moving. So mathematically, that's what makes sense. You stand on the floor, weight is pulling down on you. Well, the floor has to push back with the same force, the weight, but this time it's pushing up instead of what you're doing, which is pushing down. That's exactly what the third law says. No matter the situation, if one object pushes on another, that second object must push back. Not only does it push back, but it pushes back with the same exact force, but in the opposite direction. So, there are a few problems we can consider which makes use of this concept. Here's the first big problem we can do. Let's say we have a series of boxes. Here's box A, here's box B. Let's say box A has a mass of 5 kilograms and mass B has a mass of 10 kilograms. If you push on box A, giving a force of, let's say, 60 newtons, then I could say, with what force does box B push back on box A? So this is box A, this is box B. You're pushing on box A. There's two boxes, they're right up against each other. You're pushing on this first box. And the question is, how hard does box B push back this way onto box A? What is this force? That's the problem we want to solve. This is a Newton's third law problem, because the first question one should ask is, well, how do we even know that box B pushes on box A? All I know is I'm pushing on box A. So why must there be some force because of B onto A? And the reason we know is Newton's third law. Consider it like this. I push on box A with this 60 Newton force. What happens? A wants to move because of F equals ma. It wants to accelerate to the right. However, there's box B in the way. So what does box A do? It pushes against box B, trying to move. Well, if you know that box A pushes on box B with some force, I don't know what the force is yet, but it pushes with some force, then the third law says box B must push back with the same force. It's the same as saying, I, as the outside person, push on box A with a force of 60 newtons. Well, that means box A must push back on me as well with 60 newtons, right? Just like you stand on the floor, you apply your weight to the floor applies the weight back at you in the opposite direction. So that's the reasoning here. I know box B will push on box A because since box A is trying to move to the right, it runs into B. When it runs into B, it's applying a force to B, trying to move. Third law says, since A pushes B, B must push back. Okay? If I want to know how hard does B push, then really it's the same as asking, well, how hard does A push? Because if A pushes B, B has to push A with the same force. That's equal and opposite. So really the question being asked is, how hard will A push on B? Once I know what that force is, I'm golden. I've got the answer. So how are we going to do this? Well, what you're going to see if you look this type of question up online or in textbooks, there's different ways of going about solving this style of problem. When I was a student, I came up with my own intuition about what to think, and that served me pretty well over the years, so that's what I'm going to show you. How do I personally think about this problem? Here's my logic. I say, okay, pretend you're the person pushing on box A. Close your eyes. You can't see that the thing you're pushing on is a small box which is against a big box. You have no idea. You're just pushing on something. Okay? So what you can do is you can say, okay, F equals ma from you pushing on box A. What are you doing? You're applying a force of 60 to something. Okay, so that's the force acting on A. What's the mass of the thing you're applying the force to? Well, remember, if you're closing your eyes, you can't tell that this is actually two different boxes that are up against each other. You think it's one big box. You can't see the fact that it's really two different things. So to you, as you try to push this thing, you feel that you're pushing a big box whose total mass is 15. The 5 plus the 10 added together. Now, someone on the outside looking at what's going on, they could see, well, really, technically, he's only pushing on A. But you if you're closing your eyes, you feel the whole thing. You're pushing this whole system. So to you, your F equals ma says, I'm applying 60 newtons of force to this thing. How heavy does this thing feel? It feels like a 15 kilogram object. Okay, and that'll give rise to some acceleration. So what we can do is we can figure out, if you apply this 60 newtons of force, the two boxes together, that system will move with an acceleration. They'll move together. It's not like, well, box B will move faster than box A. No, they're up against each other. They're going to slide together, obviously. So what acceleration will the two boxes feel? I just solved this little equation here. Acceleration is 60 over 15, which is 4. All right, so what do I know? I'm applying a force to this system. The system has a total mass of 15, so the system will move with an acceleration of 4. All right, that's one thing I know. The other thing I know is the two boxes are not just one system, it's actually two separate boxes, but they have to move together. There's no reason that box B or box A will move faster than the other because they're together. When you push on box A here, we know what happens in real life. They'll slide together as one thing. So that means this acceleration I just found is the acceleration of B, and it's the acceleration of A. They both have the same acceleration, and that is 4. So both boxes will feel an acceleration. They're both going to be 4. They move together. Why do I care about that? Well, the reason I care about it is because now what I'm going to do is I'm going to look just at box A by itself. And what I'm going to say is, I'm going to apply a force to box A. Box A has to use some of that force to move with his acceleration. That doesn't mean he's going to use all of the force, but he has to use some amount of it. Whatever amount of force he has to use to get to his acceleration is his force, and whatever's left over, if I push harder than that, then box A is going to push on box B with that leftover force. So for instance, consider box A and box B, they're two different people. Person A can eat 4 pieces of pizza, and person B can eat 10 pieces of pizza, or whatever. If I give person A a whole pizza of 8 slices, he's only going to eat 4. And so whatever's left over, he's going to give to person B. Okay, even though I gave A whole pizza, he only took 4 pieces of it. Same thing here. I'm giving to box A 60 newtons of force. But he may not need 60 newtons of force to get to his acceleration. Let's find out. How much force does he need? Well, we use F equals ma. We say, how much force does he need to get his mass, which is 5, up to his acceleration, which is the 4 we just calculated. And that tells me he needs 20 newtons of force. But I gave him 60. So what does that mean? That means A uses 20 out of the 60, and the 40 newtons that's left over is what A gives to B. How do I know? I do this. I say, what's the total force given to A? He was given 60. How much did he use? 20. So I subtract. 60 was given to him. 20 he used. I'm left with 40 newtons. A gives to B. And now I'm done. Remember, I want to know, what does B do back on A? How hard does B push on A? But I said, well, I'm going to be smart. I'm going to use the fact that the third law says if A pushes on B, B pushes on A with the same force. So if I want to know what B does, all I have to figure out is what does A do? Because B is going to do the same thing. And here I just figured it out. I figured out A has an acceleration of 4. And then I calculated, well, how much force does it take for A to get up to that 4? F equals ma, his mass is 5, his acceleration wants to be 4, he needs 20 newtons of force. And then I said, well, I gave A 60 at the beginning, he only used 20 of it, so there's 40 left over. That must mean A pushes on B with this leftover force of 40. But by the third law, if A pushes on B with 40, then B pushes on A back with the same 40. And that's a third law problem. Now this is my own intuition of how to solve the problem. You may see other professors online or in textbooks or whatever solve it in a slightly different way. But at the end of the day, we're going to have the same answers. I have found this logic makes the most sense. And again, I'll go through the logic one more time. I want to know what B does to A. And I say, well, I know what the third law says. The third law is a conceptual idea. What it says is if A pushes on B with some force, then B must push back with the same force. So if I ever want to know how does B push on A, it's the same as asking how does A push on B. And then my method of finding that information, the first thing I do is looking at the system as a whole. So the whole system, meaning both boxes are now together. I'm closing my eyes. I'm going to push on this system with my total force. And then I say, if I give this force to the system, what will the system's acceleration be? So I use F equals ma and I calculate the acceleration. Then by intuition, I know that if the whole system has an acceleration of 4, then each little piece of the system has an acceleration of 4, because the whole thing moves together. So that means little box A has an acceleration of 4, and box B has an acceleration of 4. And then I put that to the side. The last piece of intuition or logic I use is I say, all right, if I want to know how hard A pushes on B, then really what I want to find out is, of the force I give to A, how much does he use up? Because whatever's left over, what he does not use, that's what A gives to B. And that's what I want to know. So I say, all right, let's look at just box A by itself. F equals ma on him. I gave box A 60 newtons, but we're not going to look at that. All we're going to look at is if box A has an acceleration of 4, what force is required to do that? So what's box A's mass? 5. What's the acceleration he needs to get to? 4. So 5 times 4 is 20. That means A, whatever I give him, is only going to use 20. Once I figure that out, I say, all right, what was he given? The total of 60. Subtract off what he used, which was 20, and I have 40 left over. If that's the leftover force, that means A pushes on B with this leftover force of 40. And then the final step is, by the third law, if A pushes on B with 40, B must push back with 40. Okay? Obviously, going through the logic like that in words takes a lot longer than to actually do the problem. But I want you to make sure you understand what the logic is saying. Why are you doing the things you're doing? What I find a lot when people are doing this at the beginning is they do this step completely right, and then they get to this step and do it right, but then they say this is the answer. They say, okay, F equals ma, 5 times 4, that's 20. So 20 is what A does. That's not true. This is an important step, but all this tells you is how much force does A need. The big step is right here. Once you figure out how much A needs, you have to subtract it from what he was given. Once you subtract it, now you know what A gives to B. All right, let's try another example. Slightly different story, but you'll see it's basically the same type of thing. Here what we have is a nice flat table. And we have a series of boxes. And these boxes are connected by ropes. All right, let's say this first box has a mass of 4, and the second box has a mass of 6. If I pull on this first rope, pulling to the right, with a force of 100 newtons, then what I'd like to figure out is what is the tension in this rope over here. So let me go over that a little bit. The system is 2 boxes. There's a rope connecting the 2 boxes. Okay. Then on one of the boxes, the 4 kilogram box on the right, there's another rope, and I'm pulling on that rope, pulling the whole system to the right. And I pull with a total force of 100. The question I'm going to ask is, in the rope between the boxes, what's that tension? Now, in order to solve that, you first, of course, need to figure out what does tension mean? What is tension? Well, tension is just a fancy word. Engineers have made this up. It just means force. Whenever there's a force which runs through a rope or a wire or a chain or anything like that, that force is called tension. Okay? So if you see the word tension, just think force. So in this case, as I pull on the system, this block number 4 is connected to block number 6 with a rope, and there's some tension in the rope, meaning 4 is pulling on 6 with a force that we call tension. And I want to know, what is that force? So how do I go about solving this style of problem? I am actually going to do it exactly the same way I did my previous example. I'm going to say this. I'm over here on the right pulling on the whole system. If I don't look back at what's going on, I can't tell that the object I'm pulling on is really 2 different boxes connected by a rope. I think it's just one big thing whose total mass is 10. So, looking at the system, the whole thing, I say F equals ma. I'm applying a total force of 100 to my system. What's the total mass of my system? Well, of course, it's 6 plus 4. 10. And this will give rise to some acceleration of the system. So I want to solve acceleration. 100 divided by 10 is 10. All right. So I now know this whole system is going to accelerate to the right with an acceleration of 10. That implies, since everything's connected by ropes and all of that, that each piece of my system must also have this same acceleration. So block 4 is going to have an acceleration of 10. Block 6 is going to have an acceleration of 10. They're moving together because they're connected by a rope. Next, what I want to say is this. If I could figure out how much block 4 requires in force to get to his acceleration, then all I have to do is say, I gave him a certain amount of force, he only uses this much of it, whatever's left over is how hard he's pulling on block 6 with tension. So we look at block 4. For this block, F equals ma. I'm wondering how much force does he need? So, okay, well, what's his mass? His mass is 4 kilograms. What acceleration does he have? He has an acceleration of 10. So, how much force does he require? He needs 40 newtons to get up to his acceleration. Good. He needs 40, but what was he given? He was given 100 by my force. He used 40. What's left over? 60 newtons. That leftover force is what 4 must be pulling on 6 with. So, the tension must be 60 newtons. That's the leftover force. And what you're going to find is every problem like this, or using third law stuff, is done in this manner. You look at the system, figure out the total acceleration. Once you know it, you now know every piece of the system has this acceleration. So then you could look at each piece separately. In this case, I looked at 4. What's going on with 4? How much force does he need? F equals ma. His mass times his acceleration tells you how much force he's going to use. From there, you say, what force was he given? In this case, he was given 100. How much does he use? 40. 60 is left over, so the tension in his rope must be 60. Let me do one last example. Very similar to the one we just did, but it's going to have one extra block. So again, here's the table. Block, 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 with ropes connecting both. This is called T1, this was called T2. And I pull on the system to the right. Let's see, let us say this guy has mass of 10, mass of 5, mass of 15. And I'm going to pull with a force of, let's say, 100 newtons. The question is, find T1 and T2. That is, you have 3 blocks. Each block is connected to another by a rope. You pull on the system to the right. There's going to be a tension in each one of these ropes. They may be the same, they may be different, I don't know. The question is, find the tension in each rope. Well, I just want to do this the same way I did the other problem. I'm going to look at the system as a whole first. System. F equals ma. I'm applying a force of 100. If I don't look behind me, I don't see that there's 3 separate blocks. It's just one big thing. And that thing has a total mass of 15 plus 5 plus 10. And that'll give rise to an acceleration a. So I want to solve this for a. So I take 100 divided by 5 plus 15 plus 10 is 30. So 100 divided by 30, acceleration is 3.33. Okay. So now I know the acceleration of my system. This whole thing will be moving to the right with this acceleration of 3. Now, I want to first, let's say I want to find T1 first. I'm going to use the same logic I did before. I'll look at block 10, the first one, and say, how much force will he require to get to this acceleration of 3.33? I know I give him a total force of 100. He's going to use a certain amount. Whatever's left over must be what he gives to the next block by tension 1. So let's do that. Block 10 first. F equals ma. How much force does he need to get his mass of 10 up to his acceleration of 3.33? Obviously, it's 33.33 newtons. That's how much force he's going to require. What was he given? Well, I pulled on him with a total force of 100, so he was given 100. He uses 33.33 of it, so what's left over is 66.67. So, tension 1 must be 66.67. Right? Block 10 uses 33. He was given 100, so he gives to the next block whatever this force is, the leftover force. So T1 is now done. Now I need T2. We'll just do the exact same thing. Let's look at block 5. He's going to be given a certain amount of force, 66.67. He's going to use a certain amount. If I take away from the 66.67 how much he uses, the leftover is what he will give to the last block. So, block 5. F equals ma. How much force does block 5 need to get to his acceleration? Well, his mass is 5. His acceleration is 3.33. Thus, he requires 16.6, say 5 newtons. So he needs 16.6 newtons. How much was he given? Do not make the mistake of he was given 100 newtons, because he wasn't. Remember, the force that block 5 feels is this T1 I just calculated. That's all he feels. Because block 10 already used a certain amount. So block 5 is only going to feel what's left over, which is a 66. So 66.67 minus the amount he needs, 16.65, and we get 50. Let's say 0.02. Of course, there's rounding here. If I didn't round, then the numbers would be a little prettier. But this 50, that's how much left over block 5 will pull on block 15 with. So this must be my T2. And now we're done. We have T1 and T2. Now, here's the thing. If you want to check your work, there's an extra step you could do just to make sure your answer is correct. And I'll show you the check. The check is this. Let's look at block 15. It better be that block 15 needs 50 newtons to get up to his acceleration. Because if I give the system 100 newtons, all 100 newtons has to be used. I can't have any leftover force at the end, or it can't need more than 100. It has to use exactly what I gave it. So let's ask the question. F equals ma for block 15. How much force does his mass of 15 need to get to his acceleration of 3.33? And the answer better be 50. Because that's what he was given in T2. Well, because of rounding and stuff, you get 49.95, which that is the 50. So indeed, this checks out. This number better match that number. Again, rounding, because it's not really 66.67, it's 66.66666 forever. But you can tell these are the same numbers. And that will always hold true. If you look at the previous example, we could do the same check. I found out T1 is 60. Well, let's check. Does block 6 need 60? Because that's what he's given, so he better use it. So we'd say F equals ma on block 6. His mass is 6. His acceleration is 10. He needs 60. Good, that's what he was given. So it works out. So this green thing I'm doing, that's just a check. That allows you, if you have extra time, to make sure you did everything right. If you made a mistake on this problem, then when you do this green check, you're going to get a completely different number. And if that number doesn't match your final answer, your final tension, then you know I must have done something wrong somewhere. Let me go back and make sure, make sure that I did the subtraction. I didn't just take this number here, or something. But you'll find if you do everything correctly, your check at the end will always come out to be the same number. So anyway, these are third law type problems. Pretty much when I give you a problem, this is what they're going to look like. It's either going to be this style where the blocks are connected by ropes, or this first one where you had two blocks are kind of pushed up against each other, and you want to know what's the force between them. So practice these. I know some of the practice problems are like this as well, and just make sure you're comfortable with it, because you'll probably see a problem like this on the test. But anyway, that's it for this video. I will see you next time.